In 2D motion, we have three very important concepts. One of them is projectile motion, and the second one is motion in a circle, mostly a uniform circular motion, and the last one being relative motion. And let's start with projectile motion. Projectile motion involves two separate dimensions. The horizontal dimension has a constant velocity, and the vertical dimension has a constant gravitational acceleration. So the vertical dimension is the same as the free fall's only dimension, and now we have another dimension added to it. So we're using x for horizontal and y for vertical. So here's the formula. So x as a function of time is equal to x0 plus v0's x component times t, and this is also written as x0 plus v0 cosine initial angle, this whole thing, times t. Let's put some parentheses here. And the y as a function of t is y0 plus v0 yt minus 1/2 at squared. So you can also expand the v0y as v0 sine initial launch angle times t. Sorry, that's not an a, that's a gt squared, minus 1/2 gt squared. And then also a vy, because vx doesn't change, so vx is the same as v initial x. So vy is v initial y minus gt. We can expand this into v0 sine theta 0, then minus gt. So we have three formulas. And the parameters we have, the positions, x, y's, initial finals, right? Velocities, x initial, y initial, and y final. X final is the same as x initial. And also there's a time. Acceleration is known. So with this, we have more formulas and more unknowns. So let's give it a try. We'll draw a diagram on the right side. So we just try to recall what we did in the projectile motion lab. So we're launching balls horizontally or at an angle. We've done both. So let's think about launching at an angle. So we're launching the ball from this origin here, and we're launching it this way. So it comes down, hits the ground somewhere below. So maybe let's remove this line here so we can remake the origin. Sorry for changing my mind. I think this makes it better. Y, x, and here's the origin 0, 0. So we have a starting point with a starting height. This is y0. And we also have a starting horizontal, which we lined up with the horizontal x. So x0 is 0. And then we have an initial velocity v0. That is a v0 magnitude and also its initial launch angle. That's a theta 0 from the velocity vector to the horizontal. And then we land here. So this is the x, and y is equal to 0 because where we put our origin, and y is on the ground level. And again, just imagine there's a big hole, so the ball will just continue to move below the ground level so that it doesn't get stopped by the ground because there's a hole. So we're asking how fast it is right here. So I know that it's probably pointing this way, the velocity vector, right? I don't really have space for it. So let's move these over here. So that's for this, and as for the velocity, it points downward. Final velocity. Okay. So let's give some numbers. In our lab, we had the initial velocity v0. We know that v0 is roughly 5 meters per second, and the y0 is about 1.2 meters, and the angle, let's say 38 degrees. So the questions we're going to ask, how far is x, right? How far does it land horizontally away? And how long does it take? And also, what's the final velocity equal to? Magnitude. And what's the angle the final velocity makes with the horizontal? So let's mark the angle here. That's angle. Okay, so let's have the a formal list for the parameters. We'll start from x0 equals. We'll set our origin at here, so x0 is 0. So then x is equal to, that's an unknown. And then y0, the height right here, 1.2. And then y is equal to, at the ground level, right, landing on the ground level, 0. And then v0 of x is v0 cosine 38 degrees. So 5 cosine 38 degrees. We'll calculate that. And let's move it down here. Initial y is equal to 5 sine 38 degrees. So we'll calculate that. And these are the initial velocities. So we have the final y velocity, which is unknown. We also have the time is unknown. Okay, let's check all the parameters. We also don't know the final angle, but once we have the final y velocity, we can combine it with the initial x velocity, which is also the final x velocity, because x doesn't change velocity, right? So once we combine those, we can get the total v, we can get the total the angle theta, right? So v equals, I like to put these in a box because these are not independent unknown parameters. Once we have the rest, we can calculate these two. So we simply have 2 x's, 2 y's, 2 velocities, and then 2 other things, another velocity and time. So we have 8, right? We have five unknowns and 3 unknowns, 5 knowns and 3 unknowns for the 3 equations to solve. Okay, so let's start plugging the values in, starting with x position here. So we have x equals x initial plus v initial x. Oh, forgot I should calculate these. So go to Python. So 5 times cosine 30. 5 times cosine 38. 5 times sine 38. Okay, I got that. So x is 3.94, y is 3.08. Alright. So 3.94 t. And that's it, you can't really solve it. So I'll leave it and go to the next equation, y. Y final is landing on the ground. Initial is 1.2 meters high. Plus initial velocity y 3.08 time minus 4.9 times squared. So this is again a quadratic equation. I can solve this equation and get the time. 1 minus 2a minus b plus minus b squared minus 4, this a carries a negative, so positive that, for AC, oops, preview here. Okay, so I'll use my Python calculator to get this done. I think it's called quadratic. Okay, it's not focused. Okay, quadratic. Just call that function. A is minus 4.9. B is 3.08. C is 1.2. Okay, I have two answers. 272,901. Negative 272. So we'll take the positive. Okay, so now we have the time. We can plug this into that previous equation and solve. Let's bring everything to the left side. So this x is equal to 3.94 times 0.901. We can bring our Python back. And we use T2 times 3.94. Okay, 3.55. That's that 3.55 meters. So we found out the horizontal distance. Okay, so that's check. And we also found the time, check. So now the final velocity. So let's save some space. Let's keep writing. Vy is equal to initial y, which is 3.08. 3.08 minus 9.8 times time, 0.901. Okay, so 3.08 minus 9.8 times, I remember that was T2. Okay, so this gives a negative velocity, which makes sense. Our ball is coming downward, so 5.75. So negative 5, let's rewrite that. Negative 5.75 meters per second. Okay, now we have pretty much all the ingredients we need to calculate for the final total velocity. So let's go ahead and calculate that. First, we know that the velocity final is equal to, in magnitude, velocity final in x squared plus velocity in y final squared. Because x does not change velocity, we can still use the initial x velocity squared, and then we already found out the final y velocity, so we can square that. This is 3.94, and this one is 5.75. Remember to never square negatives. Okay, so we'll leave it so we can batch calculate using our Python, and the angle is equal to arctangent y over x, so Vy or Vx, or arctangent Vy over V initial x, right? So we can find out using these two values again. So we'll do this in Python. All right, so we'll use this function here. This is Pythagorean. This is also something I wrote myself as a convenience function. So if you have 2 or 3 parameters you want to find the magnitude, you can do this. Okay, so we have 6.97. And we'll find the arctangent A10. The Vy is a negative quantity of minus 5.75. Vx initial is 3.94. So we have a negative angle, 55.6 degrees. So 556, the other is 697. Negative 55.6 degrees. So it's 55.6 degrees below the horizontal. So that's how you typically do a projectile motion problem. And the next motion to review is uniform circular motion. Okay, we already know the formulas. We have an acceleration centripetal. That doesn't look good. Which is equal to angular velocity squared times r, or linear velocity squared over r. So that leads to this relationship between the linear velocity and angular velocity. So in this motion, the acceleration is pointing constantly toward the center. So that's the centripetal. So uniform circular motion with, let's draw a circle here. Let's see how good I can draw a circle. Oops. It's better than I usually do. Okay, so we have this circle. We'll have an x and y axis. Alright, so we have x and y axis. And we'll pick a point here to indicate where the object is. And this location can be called r vector. Our origin. So let's imagine the object is going this way around the circle. So at this point it's going upward towards the left. So that is the velocity vector pointing this way, and acceleration toward the center. So acceleration points this way. So as it goes around the circle, its location changes. So does its direction of velocity. Say now it's here. So now it points toward the left and downward with its velocity, and acceleration still points toward the center, like this. So you can draw this anywhere you want. The property is the same. The acceleration keeps changing direction, but the magnitude stays constant, and the velocity keeps changing direction, and its magnitude is constant. So that is our uniform circular motion requirement. So uniform circular motion. This is defined, or aka uniform, so omega is equal to a constant. You can also say v is equal to constant, and circular is this r is equal to constant. So that's the same as the definition of a uniform circular motion. So for this part, what you're supposed to understand is, for example, if you increase the radius, how does that affect your uniform circular motion? If you let's imagine it was easy to do. Say you're driving, then you could maintain a constant speed. That's easy. You just watch your speedometer. So if the velocity is constant and your radius goes to twice the radius, okay. So what about the acceleration required? So acceleration And because this is constant, that goes twice as big, the whole fraction will be half as big, so only half as big as the original. So you need less acceleration toward the center, which is provided by partially by banking of the surface you're driving on. If there's no banking, then it's entirely provided by friction. So if you can round a circle with a larger radius, then you need less acceleration or less friction, then you will be more likely successful rounding that circle. So that's one likelihood. Say you're driving, so you can easily maintain your velocity, your speed as a constant. But if you're on a rotational platform, this can be a constant easily because you can maintain a constant rotational speed. So if you're on that platform and you're going from radius r, you just go radially outward, you get slung out. Maybe you just decide to move outward. I can imagine maybe a carousel or something. So let's see. So what this does is this one now is a constant and that doubles. So the acceleration with a constantly rotating constant angular velocity platform, now it doubles. So this really depends on what's convenient to do in such a motion. So this is I would say multiple choice type of questions, almost just conceptual. If we didn't add the centripetal force in the Newton's law application chapter. Alright, so if you wish to maintain a constant acceleration magnitude, then you can just have these factors play out. If you double the speed with a constant acceleration, what is the radius you have to go, right? Okay, so the last part is relative motion. Okay, this part may not be required, but I'll review here anyway. Relative motion is an interesting, just an application of kinematics and vectors. So in the past we have been just giving velocities with respect to what. If you're moving, your velocity measurements are going to change. So these velocities are with respect to a default reference, which is the ground. So if we recognize that every velocity measured has a reference to an assumingly non-moving object, and it is measuring another object. So every velocity has two objects involved. One is the reference, or the person who does the measuring, I would say experimenter, and then the other velocity involves the observed object, the object that moves, right? So we can keep track of that using subscripts. That we have two subscripts. One is the velocity of the observer. The other is the velocity of the observed. And there are multiple ways to do this. For example, you have a car A. Here's an A. This is a car is moving. And you also have a car B. This car B is also moving, maybe with a higher speed. And so you can observe the car B from car A as car B is pulling away from car A, right? There's also here, this is seemingly non-moving ground. So here's the ground. So there are three observers. Let's just say that there's one person, a physics student, riding in car A, another one in car B. They are named after the cars they're in. And then there's a third person standing on the ground, so the ground person. And we can calculate let's describe the velocities first. So let's first describe car A speed like we usually do with respect to ground. So VA with respect to ground. Or sometimes we just do VAG, depending on the textbook you use. Normally the left one is the observed, the right one is the observer or the reference. And we can also do car B, velocity of car B with respect to ground, or VB ground. So these two values are the speedometer values, hopefully accurate speedometer values on either car. And there's also a, say, velocity B with respect to A. B is pulling away from A, so B might be, say, 5 miles per hour faster than A, or maybe 5 meters per second faster than A. So this is relative, right? B measured by A, so A observes B. So let's just say this is equal to 5, and we can ignore the unit. And this is A with respect to ground. Let's just say 55 miles per hour. Let's just imagine that. And B is 60. So we observe that B pulls away from A at 5 miles per hour, right? So that makes sense. And we put them all together. We have V B versus ground is VB versus A plus VA versus ground. So we can see these two. The measured is also the measure, the observed. Let's just call it the observed plus the observer. So this observer and observed goal, the duality of this goes away, and you only have the B and the G, right? So that's how they are combined. And this is a one-dimensional example, but it applies to 2 dimensions or 3 dimensions as well. So that's how we do relative motions. And in certain relative motion questions, you could be asked to combine velocities, such as an airplane, for example. An airplane has, so example, with airplane, we'll have the airplane's velocity versus the air, because it's flying in the air, so it's speedometer per se is showing how fast it moves through air. And also there's the air moving against ground, so that could be the wind, right? And there's also the ground speed of an airplane. If you ever have been on a longer flight in an airplane, it typically displays in between entertainment, it displays how fast the airspeed is and how fast the ground speed is. And the closer they are, the you know that they are, there's no wind. So these two speeds are relative to, they're related to with this. So we can say the plane versus ground is actually the plane versus air plus air moving against ground. So if this is given, the direction could be different. For example, if the airspeed is you're flying due east, but there's a wind, maybe there's a wind like this. Oh, so then what is your actual velocity? Well, it's going to be the vector sum. So this plus that. And if you draw something, maybe something like that. So, although your plane's nose is heading towards east, is being blown to the north. So it drifts to northbound. But if you don't wish to do that, then you could have, say, if you wish the total to be this direction, and you still have the wind blowing against you, then you cannot just fly forward. You have to fly with an intent to add and result in an eastbound direction. So you have to have something that does this. See, the vertical component of the wind, or the y component of the wind, this direction, has to be countered by a y component of the airplane flying. So the airplane has to fly with a y component downward like that. And if your airplane has a fixed speed in the air, same as that length, then you have to fly in this direction. just say that these two lengths are the same. So that this component forward, that component, okay, southbound, for example, to counter the northbound wind dragging you, and also the wind is pushing you back, right? So if you add these two together, that gives you the total velocity. I bet it's shorter than that, probably this. All right.